So warm welcome to all four of you. May I have your names? Okay, all right. Okay.
Matt?
Okay, I've been in touch with you, Matt, I think over email. Yeah. Okay. All right. Yeah, so warm welcome to India, to Bengaluru and to IISc campus. As you know, only today's class will be in the aerospace department. From tomorrow we'll be having a virtual class on Tuesdays and Wednesdays, and Thursdays we will be having the classes in CVH. Yes.
How do you want us to set it up? Do you want one of us to attach to
I think JVR, Professor Prasad has brought a laptop, and he will set it up and connect it to the projector over there, and he's also got a microphone so that we can have it interactive because these are synchronous virtual classes. And Fanindra, you can just go to the CVH on Tuesdays and Thursdays also same time. Tuesday and Wednesday. And Monday and Thursday I'll be here for, again, all 4 days it will be in CVH at 11. Yeah. Okay, so let's start with this course. I guess all of you are done, I think, except one of you, the deformable bodies, COE 3001, which is a prerequisite for this. So in case you get stuck up with certain concepts or certain terminology, do just raise your hand, let me know. I'll try to explain that as quickly as I can without getting into the rest of the time. But because it's very important that you understand the terms. See, more often than not, almost all the subjects that we study is essentially the physics and the maths that we have learned in our high school. It's just advanced versions of that we learn in engineering. But the only main difference is in terms of the terminology. You have a little more terminology, especially those associated with aerospace engineering in our courses. And therefore, some of these things might be something that you already know, just that you might not know in those words. So it will help if you just don't understand anything. Absolutely feel free, because it's a very small class. We can make it as interactive as we can. And hopefully Professor Patil will be covering some of those topics which you might need here within the time that I start talking about it. But nonetheless, absolutely feel free, either in class or even outside. Yeah. Okay. So there's a reason why this is an AE course, whereas the 3001, which is the prerequisite to this, is a College of Engineering course. So in other words, that's a COE course because that's something which is much more broad-based, more generic, and that's something that we want to look at probably from a point of view of application in any field of engineering for that matter. Whereas here we are having it specifically AE because we want to make sure that this is kind of applied to aerospace engineering. So throughout this course I'll be talking about what are known as flight vehicle structures, to make it very generic. Any kind of aerospace vehicles, be it aircraft, helicopters, be it rockets, missiles, or even satellites and interplanetary vehicles and things like that. So whatever we study over here will be more broadly applicable that way. And in fact, to give a step further, it can be a little beyond aerospace as well in terms of any kind of transportation structures. So if you're looking at marine kind of vehicles, be it ships or yachts and things like that, or you're looking at trains, railway kind of constructions, essentially all of these have a certain structure, and a way to analyze that is what we are trying to look at over here, and that's essentially what is the focus of us here. So by analysis, we essentially mean we are trying to break the problem into certain smaller parts which are much more easily kind of tractable compared to the overall problem, and therefore we are trying to see if this can be addressed in a much more intricate way. So whereas that is analysis, the place where I come from is essentially the lab called, abbreviated as NMCAD, where we deal with not only analysis but also design. Okay, so whereas analysis is something that, as I said just now, we are breaking a bigger problem into smaller parts and trying to look at how we can address each of those parts, and then we are trying to stitch them together. This is what design does, is more of a synthesis. So the next step to analysis for most people working in engineering is to take that whatever knowledge we gain out of analysis, either we study or we do it on our own, and then we see how that can be translated into design. And that's essentially what we do at our lab, where we focus on both analysis as well as design. So some of the students, so you see two of our PhD students over here, Fanendra, who's with the camera, and Chinababu. So Fanendra will be your TA for this course, and we have another course, as you know, dynamics in the second half, which you would have already done, and so some of your other classmates or other juniors are going to take that, the sophomores, and they will be looking at Chinababu as the teaching assistant for that particular course. Sorry, do I have it wrong? Interchanged, okay. So I think this is from the last last year's slide. So Chinababu was the TA for the structural analysis. So just ignore this. I think Fanindra is on the group email that I sent to you, and so you can get in touch with him on that, okay. Now, it's important for you whenever you're learning a course from an instructor, irrespective of it being the same course, in this case 3140 that we're talking about, depending on who is teaching it, there will be certain nuances, okay, and this is what you would expect. Having graduated from high school and getting into engineering, you would have seen in the first few years itself, depending on who teaches it, they will bring in a certain flavor to it based on their own whatever career backing they have, what kind of things they have worked on. The fundamentals will remain the same, the equations will remain the same, but the way they convey it, with especially the kind of examples that they give in terms of real life applications, etc., it's going to be a lot which is based on the individual teacher, okay. So it's from that point of view, I'd like you to know that the lab that we come from is NMCAD as for short form. So I'd just like to rush you through some of the aspects of it very briefly before we get on to that. So starting with C, analysis and design, we already talked about. Analysis, splitting the problem into multiple parts and trying to tackle each one of them individually. Design is essentially synthesizing that and trying to put together to get the holistic picture. Probably it could be a part of the entire vehicle design itself, but essentially you're looking at how you're going to apply those things which seem like disconnected, seemingly disconnected parts you're trying to bring together for a practical application. So that's where design goes. Now, if you look at, and we will look at probably towards the second half of this class itself, the introductory class that we are having right now, there are certain very, very important differences between aerospace engineering applications of structures and any other engineering applications. In between would come the other kind of transportation structures that I talked about. But if you look at static structures, like this building itself is a structure, right? Or a bridge is a structure, and so many civilian structures that you're familiar with. All of these have more of a static nature. In other words, yes, of course, very tall buildings might be swaying a little bit with the wind, or if there's an earthquake, you could have fairly large vibrations. So there will be certain dynamic loads there too. But in a vehicle, and especially a flight vehicle, a flying vehicle, be it in air or in space, you're going to have much larger dynamic forces, okay? So dynamics is going to play a much more critical role, but we'll see all of those differences. And when things are in motion, that is, there is dynamics, and you've already done a course in dynamics, you will see that the faster it goes, and the more people you want to carry, or more payload that you want to carry, even in a cargo or a military kind of an application, be it bombs or whatever, you are essentially looking at the vehicle itself should not bring in a huge weight penalty. So having been in aerospace for more than a couple of years now, I'm sure you all very clearly appreciate the need to be lightweighted structures. So whatever structures we are going to be dealing with will be lightweighted structures, and that's one of the reasons, as I said earlier, we are looking at an AE course, not a COE course, because that aspect has to come in. And the way it has been done historically is through aluminum alloys. So aluminum alloys amongst all metallic alloys seem to be reasonably good in terms of strength and stiffness, but at the same time the weight penalty because of their densities being low is something that is acceptable there. But over the last 3-4 decades, and more so in the last 1 or 2 decades, the transition has happened, and most of the vehicles, including passenger vehicles, are slowly shifting away from aluminum. Aluminum is still used, but not to the extent it was used earlier, aluminum alloys, but we are essentially moving towards composites. And you will see a flavor of what we are going to through in the industry throughout this course, in the sense that this is not a composites course. It's a generic structural analysis course, a very basic course for undergrads, tailored for that. But at the same time, I don't want you to be left out with something that is, let's say, historical and not of any practical use when you go to either the industry or academia or your research or higher education. It should not be something that you feel like you are at a handicap. So I will be bringing in certain traces of what are composites and why they are so widely applicable. Of course, lightweight is one of the main motivations, but that alone is not enough. It might be okay for a layman to understand it that way, but you as engineers, we as engineers have to look at a little more intricately in terms of what are the properties, which properties make one material lightweight compared to another. So it's not just the density alone, there are certain other aspects, nuances. We'll go into those intricacies in the future classes, but for now, rest assured that most of what we will be doing in this course, even though basic and fundamental, will be directly applicable to the material that is most commonly used in aerospace engineering today. For example, your Boeing 787 Dreamliner, or you have the A350 from Airbus. All of them use about 50% by weight of structural material which are made out of composites. So obviously you can't ignore that, it will be at your own peril, and even more so when you go for more performance required, performance demanding kind of applications like fighter aircraft or rockets or spacecraft and things like that. So will that mean that you will not be able to analyze metals? No, not at all, because all of that we are going to do here is not beyond failure. Once failure takes place, or let's say metal yields or a metallic alloy yields, the way it behaves is very, very complicated, much more complicated than composites. But in this course, the basic introductory course, we're not going to be dealing so much with failure. We will be touching aspects of it, but up to failure, whether it is composites or metals, they behave in a very, very similar way, just that the composites are a little more involved in terms of the models. So whatever we do for composites over here, I will also be telling you in parallel what is the simple special case of that, so that it can be applied to metals or metallic alloy structures as well. So that's the kind of approach that we will be taking. The other important thing which we'll absolutely not see in this course, but that's the nature of our research, our students and the rest whom you can meet. My office is AE109. The very next room is AE3140. So just a 1 minute walk from here across that bridge, pedestrian bridge that we have right here. So this is 105, as you know. So feel free to interact with the students and try to, I think some of you are signed up for, I think the research credits as well. So if any of you would be interested in taking that research credit with us, you're always most welcome. You can let me know at some point down the line. But the models that we focus on are those which are not linear. So linear models have been what have been the main crux in almost all of the textbooks and things like that. But over a period of time, we have seen that in practice, even irrespective of whether we go for composites or even metallic structures, including aluminum alloys, you will not be able to do well enough with linear models. So you need nonlinear models, and we're talking about nonlinearity. There are two aspects to it. One which comes with the kind of material that you use. Both in composites and metals you will have nonlinearity, which we call as the material nonlinearity. And the other aspect is in terms of the geometry, and that's another significant important thing which most people ignore when they talk about structural analysis, because a structure, remember, is something that is not just a material. material choice amongst all the options that you have is one aspect of choosing a structure or designing a structure, right? The other most important thing is after you have chosen the material, or in parallel even, you would be deciding the geometry of the structure. Okay, so always keep in mind that whereas most people, most courses and most textbooks even unfortunately will focus, when you say structures, give more importance to the material, equally if not more importance is to the geometry, and especially so when you're taking this forward to an aerospace structure, any flight vehicle structure, the geometry will be very, very keen part of the decision making process whenever you're doing a design, and therefore it will play a huge role in analysis as well. So that's something that I would like you to keep in mind, so that nonlinearity can come not only from the material point of view, it can come from the geometric point of view as well. But this is the only time I'll probably be mentioning this nonlinear word or the nonlinearity aspect, because that's beyond the scope of this particular course. But if you're somebody, some of you are intent on taking a research credit or something, maybe depending on your interest, you might look at a nonlinear model of what we are going to do here in the course as linear, right? The other aspect, which again you will not see throughout this course, and the only time I'll be probably mentioning here, is the fact that we work on what are known as multifunctional structures. So in other words, the materials that we use are not only going to do something which all materials are expected, like aluminum alloys. You want it to give a certain strength, you want it to give a certain stiffness. So the strength is so that as you increase the load, no more number of passengers or higher speed, it doesn't fail up to whatever prescribed requirements are there. So that's essentially what you're talking about from a strength point of view. But there is also a stiffness requirement, in the sense that you do not want it so flexible that it's probably, for example, on landing or takeoff, it's touching the wing tips are touching the grounds, right? So but you would have seen, if you had just seen out of the window when you are flying out to from Atlanta to anywhere in between and then to Bengaluru, you would have seen that the wing tip deflection is fairly large. It could be of the order of a few meters, but yet it is flexible but not overly flexible. It is stiff but not underly stiff. So stiffness requirements are also there. But both of these, strength and stiffness, and we will soon see there's another important S, which is stability. I'll go into the aspects of that later. But for now, understand whether it is strength, whether it is stiffness, or whether it is stability, these are essentially load-bearing functions. So it's a single function, or what we call as a unifunctional material. Okay, so aluminum alloy is an example of a unifunctional material. It does very well as far as that is concerned. Many composites also do even better than aluminum as far as that is concerned. But in our lab, in our research, we take this a step further and we see if can we add an additional functionality to it. Now remember, just as I mentioned earlier today, the reason why we went from aluminum alloys to composites is we wanted even more lightweight structure. Same strength, same stiffness, and even lighter structure. Or the other way around, have the same weight but have a greater strength and a greater stiffness, so that you have a more capable vehicle which can fly probably farther. It can probably fly more people or more cargo, and it can probably fly at a faster speed, or combinations of these kind of things. So essentially we are trying to go towards that. But both of those cases, and this is what is on all flying vehicles today, you have unifunctional materials, only load bearing, though there are aspects to it like strength, stiffness and stability, which are part of the load bearing function. But we take it a step further and we deal with materials which deal with additional functionality. For example, Fani Indra is working on certain electromagnetic properties that you would like to build into them, so that you can have stealth materials. So these stealth materials, instead of just being coatings or whatever, can you make the structure itself respond electromagnetically in such a way that it doubles up as a radar, instead of having to carry a separate radar as you have on AWACS kind of aircrafts. So you would want to see, can you build in that functionality? Another example is, can the structure be a battery? Typically, a lot of electrical requirements are there in the aircraft, and both in the cabin and for the actual flight itself, and you typically have huge batteries, both in terms of volume as well as in terms of weight, which are carried on aircraft. So can you replace some of them if the structure doubles up as a battery as well? Okay, so what are the implications, what are the repercussions of that, what are the safety issues associated with that, what happens when there's a lightning strike, etc. So those are kind of things that we look at. That's an additional functionality which we call as energy storage, because that's what your batteries do, whether it's your mobile batteries or your laptop batteries. Essentially that's what it's doing, to store energy. There could be something like energy harvesting, because these are vibrating at a certain level. Can you harvest a part of that energy and utilize it for the lighting that you have in the cabin for the passenger aircraft, for example? So these might seem like very small advantages that you're adding, but it goes a huge way in terms of the life cost of an aircraft. Remember, when an airline buys a passenger aircraft from a OEM like Boeing or Airbus, they're not paying just for that aircraft at that point of time, but regular maintenance they pay, and more importantly, an even higher cost is during the lifetime, the fuel costs that are involved. And the fuel burn is going to be far, far more for a heavier aircraft compared to a lower aircraft performing the same tasks with the same payload. So the idea is, in going from aluminum to composite, we are only looking at a material improvement. You're looking at a material which is better, which is lighter in weight for the same load carrying capabilities. So you're only doing at a one functional level. But now you realize that the aircraft is not just made out of structure. Okay, obviously you will not be flying an aircraft just made out of structure for fun, right? It's not like a recreational flying that you have just to prove a concept, but you want to carry payload. And the more payload you can carry, the less the weight of the structure needs to be. And which means that not only do you need to change materials like going from aluminum alloy to composites, but in the future, like say 10, 20 years down the line, you will see that you want to replace certain subsystems which are non-structural systems with the structure itself. So in other words, you're replacing some of the batteries with the structure itself. So you're replacing a radar or certain other electromagnetic communication devices with this, or certain energy harvesting kind of devices with this, so that when not only reducing the weight by changing the material, but even you're replacing some of the non-structural systems with the structure itself, which is anyway there already, and therefore you have a huge reduction in weight of the structure, and therefore you're able to carry more payload, or with the same payload you're able to fly farther or faster or both, right? So that's the direction in which most of these things are going. So that's the gist of it. As I said, that's something that will not be focusing on for the rest of the course, but just to give you a glimpse of where structures, especially from the design point of view, are heading towards, especially in aerospace, because our prime motivation is to offer the load bearing, but reduced weight, not only from a structural point of view, but from the whole vehicle's weight point of view. And this is one of the proven ways, at least from a lab level, that we can do that, but eventually it will see applications in the actual flying vehicles. So the reason why it still is not there, even though it's proven in the labs, is because the kind of stringent requirements that the certifying agencies like FAA in the US, or similar organizations in India, we call it the DGCA or SEMILAC, depending upon whether it is civilian or military kind of aircraft, and you have a similar kind of a thing in Europe or Russia, everywhere around the world. The requirements are so stringent that even for us to move from aluminum to composites, it took decades after composites were developed. Okay, so in fact composites are available in nature itself. Wood is a composite, our human bones are composites, our skin is a composite. So nature has shown that almost all these structures, load bearing structures in particular, are typically composites, and even engineering composites have been there for a long period of time. But the actual application of composites onto aircraft took a long time, because the certifying agencies need to be convinced that it's going to work and it's safe. Okay, so that's why you don't see multifunctional materials. Of course, there are certain aspects of smart materials what are a subset of multifunctional materials. You might have heard of this phrase, smart materials. Also sometimes interchangeably used with adaptive structures. So things that adapt to a situation. For example, a morphing wing. So a wing, as you know, is on the aircraft the same wing, whether you're taking off, whether you're climbing, whether you're cruising, whether you're descending, or during the cruise in between it's performing certain maneuvers, or loitering if it's a kind of a reconnaissance kind of an aircraft, and if it's a fighter, then it's some kind of a dogfight that it is going, and then it's descending, and then it's landing, taxiing. Each one of these phases will have a certain optimal shape of the wing. In other words, what is optimal for cruise might be totally off as far as climbing or takeoff is concerned. So you can't have two different wings for these, because you're not going to change those wings, right? So one way of practically achieving that is through morphing wings. So the wing in some sense changes its shape. In other words, for example, the camber of the wing can probably undergo a small change, so that when it is flying low speeds, like for example, let's say a loitering aircraft in reconnaissance, it wants to capture as much imagery of the place over which it is doing a reconnaissance, and therefore you might want a long endurance over there, which means that you might want almost zero camber, okay, because camber is going to increase your drag, and therefore it's going to have negative repercussions in terms of the fuel burn, and therefore you'll not be able to loiter for much longer. So you want almost a zero camber over there, whereas in certain other phases of flight, let's say takeoff, etc., you want to maximize your CL max, and therefore you want to see if you can have a large camber over there. So you want to change your camber along the route. So this is just one example. There could be other aspects of the wing geometry that you would want to change. That's essentially your morphing, and that's again something that can be quite effectively done by using multifunctional materials, and that's one of the other motivations that we have, and that's where smart materials come into picture. Smart or adaptive structures adapt to the environment, and essentially what they're doing is to see based on the sensors that they have. You want to see if the sensor gives a feedback, and therefore there's an actuator as well, and that actuator will make apply certain loads internally to the structure, which will make it change the camber, for example, or some other shape, so that it is optimal for that phase of the flight, right? Now, when you're looking at that kind of an application, you have a separate structure, you have a sensor, you have an actuator. But what if you can make a material which is not only load bearing function, but also is a sensor and an actuator? So it's a co-located means it's at the same location. You have both the sensor as well as the actuator. In other words, they're not two separate things. The same chunk of material performs as a load bearing structure. It performs as the sensor. It performs as the actuator. That's when you call that kind of a structure as a smart structure. Like when we, depending upon the kind of weather conditions that we are in, the kind of temperatures and pressures that we are exposed to, our body tends to adapt to those over a period of time. Okay, there might be an initial reaction, but then if you're long enough in a hotter place, or long enough in, let's say, a place with low pressure like a high altitude place, your body will soon adapt to that. So we are learning from natural elements like human body, or animal bodies, or even plant life, to see if we can not just blind copy, but if we can adapt some of those techniques that nature has evolved over millennia. Can you just adapt some of those to the applications that we want from an engineering perspective, in our case aerospace engineering. So that's essentially what we are moving towards from a research point of view. So and of course our department over here, the Department of Aerospace Engineering at IISc, it was established way back in 1943, just a year after our first aircraft industry, the Hindustan Aeronautics Limited, short form is HAL, and they have a wonderful museum. So I would urge some of you, when you during your weekends, if you're not going on a trip outside Bengaluru and you're just seeing around Bengaluru, that's one of the things you can go to, the Aerospace Heritage Center and Museum, so which is a good thing for aerospace engineers. So just a year after that HAL was established around 1942, they had a huge shortage, obviously, of manpower, and for the human resources, this department was established. And of course, our institute, IISc, is much older than that. In fact, 2009, we celebrated the centenary. Of course, not as old as Georgia Tech, but one of the older aerospace departments that we have in the country and around the world. Okay, so with that, I kind of complete this slide. If you have, also some of you had issues with the MS Teams connection, so hopefully Fanindra will help you resolve that. If not, there's also Ramesh in front of my office, so you can take the help. He's the system administrator over here, so I'm sure it will help resolve, and try to do that as soon as possible today itself, so that, because for tomorrow's class you might need it. But anyway, that will be on a common laptop, that's what JVR told me, rather than each of you individually attending from your own rooms or wherever you are. Have it all in the CVH reading room, the second floor over there, right? So that's as far as that is concerned. So I think I pretty much covered here. So any questions or doubts so far in whatever I've talked about? I've gone a little fast because it's just a very preliminaries and the introduction. So any questions? No? Okay. So let's move ahead. Okay, so now let's look at some of the topics. So as you know, first of all, the class timings 11 to 1, Monday and Thursday it will be physical, like what we're having today, but in a different location. And so this just over a month we are covering a semester, so you have to bear with me. May 20th to June 20th will be the last day of your classes, and so therefore you have to get to speed with some of these things as quickly as possible. So we are always there for you, so just try to ping us in case you have any issues, so I can immediately come and see how I can help you. As far as office hours for this course are concerned, it's absolutely flexible, as I think I probably mentioned in the email. I would like to be available to you at the earliest opportunity as soon as you have an issue. So just email me or send me a message in chat, in Teams or whatever, once you're able to connect to it, and then we will set up an appointment as soon as possible and get that done. Once in a while, if that's something that Fanindra can handle, please feel free. As I mentioned, he's our Prime Minister's Research Fellow, one of the most prestigious awards given to PhD students. So, and he's very close to finishing his PhD as well. So he's one of our smart students. So I'm sure he'll be able to, and has some teaching experiences as well. So I'm sure he'll be able to help you in resolving some of your fundamental doubts. But otherwise, you can always get in touch with me as well. Okay. Next, coming to the topics. Okay, and also jokingly, I mentioned some certain tropical seasonings because those are what I'll have in yellow at the bottom of this slide as we go. And those are things that, just like I talked a few minutes back about multifunctional or nonlinear, those are not part of your course, but unless and until you know certain terminology, at least from there, your knowledge that you gain out of this course will not be of much use. Therefore, I will give you flavors of that as well. Okay, so what are the things that we are going to actually cover in the course? One is the fundamentals of light vehicle structures. So I'll be using a few abbreviations to make the slides less crowded once in a while. So you will see this FVS coming up very often. So essentially I'm talking of flight vehicle structures, which, as I said, is anything that flies either in air or space and in any atmosphere for that matter, be it like rarefied atmospheres of Mars or very dense atmospheres of Venus or Titan, which is a satellite of Saturn. And anywhere in between, like the Earth's atmosphere, which has a density in between these, doesn't matter. The principles, the theory, the math remains the same. The numbers can be larger or smaller in different cases, but essentially you're doing the same thing. You have to make sure that it flies where it is supposed to fly, what you're designing for, what is the RFP, the requirement that you are given from the user point of view. Are you able to do that? Okay, so fundamentals of flight vehicle structures, including flight vehicle materials. Okay, so even though you might have had a course related to materials, have you had any course on materials? Yeah. So it will be more like a review, that we will not be talking of the materials in detail in this course, but materials form a very, very important part of the structure, as I said, as much as the geometry, or the geometry is actually a little more, but nonetheless we will be looking at that. So our focus will be more on the geometry rather than the materials. What do we mean by geometry? For example, if you look at this tabletop that you have here, it's not a solid chunk of material. It's of course having a reasonably good length, it's having a reasonably good width, but I don't say reasonably good thickness, right? So that would be a waste of material, right? So you're making it thin. Why? Because the kind of loads that it can still take even when it is thin. Whereas only if it is large enough from a length and breadth point of view, it will be able to accommodate more things for whatever purpose it is designed. Same thing, same logic applies to your flight vehicle structures as well when you're taking it over there. So that's essentially what we will be looking at in terms of the material and the geometry contributions over there. And once you combine this material and geometry, sometimes as plate-like structures like this, sometimes as you see in, let's say, an aircraft fuselage, the skin that is there, or in the wing that is the skin, or some of these structures like, if you don't understand some of these terms, fine, we will be talking about them in detail later. The spar in a wing. So some of these are not thin structures but long structures. So in this case, one dimension is small compared to the other two dimensions. In a spar, for example, you have one dimension, which is the length, large compared to the other two dimensions, which are the cross-sectional dimensions. And that's true with your beams in the civilian engineering structures as well, or columns that you have, which are holding up the beams that you see over here. So essentially, we will be dealing with almost this entire course, we'll be dealing with so-called two-dimensional structures. Why I'm calling it two-dimensional? Every structure in reality is three-dimensional. In other words, it has three spatial dimensions in three orthogonal directions, a length, a breadth, and a thickness, right? But one of them happens to be small, and therefore, if I am intelligent enough to play around with this model, the 3D model, I can reduce it to a 2D model and deal only with the coordinates along the length and the breadth. I don't need to deal with the coordinates along the thickness, which means that I am putting all of the material properties along the thickness. If I take at any location along this plate, I take a normal to this, it's a line, right? So that line, instead of a finite length, I'm shrinking it to a zero length, which is when instead of a finite thickness, I have a zero thickness of this plate as a whole. Okay, similar thing in curved structures also. You're essentially, instead of here you have a reference plane, you have a plane that you get there. In the case of a curved structure, you'll have a reference surface, right? So it's a curved surface that you're going to have, and then you deal with that. Similarly, in the case of a beam like this or a column like that, you want to reduce the cross. Here what did we do? We reduced the smaller of the three dimensions. The we first of all identified thickness is the smaller one amongst the length, breadth, and thickness, and then therefore we reduce the thickness to zero, lumping all of the properties which are distributed along the thickness at a point, and therefore there are many points along that, and essentially you have a plane. In the case of a shell, you have a surface, right? Same thing here. Here we reduced a smaller dimension. There also we reduce a smaller dimension, but there are two smaller dimensions. The let's say along a cross section, you have the size of the cross section. In this case, it's just a rectangular cross section that you see of the beam over here. So it is essentially the thickness and the height of the beam that you see over there. So you're essentially seeing that, can I reduce that to a point? And when I reduce that for each cross section and join all those points, I now get a straight line. Here I got a plane or a surface. Here I'm getting a line or a curve if it's a curved beam, for example, in a frame, right? So now, instead of a 3D problem, I had a 2D problem over here, and instead of a 3D problem, I now have a 1D problem. So obviously, when you're reducing the dimensions, it's called dimensional reduction, and if you do that properly, you might still get as accurate solutions as you if you are doing a 3D model. Okay, so how we go about doing that in a right way or an appropriate way with least reduction in accuracy. Always your 3D model is going to give the best accuracy if you're doing it well, right? But it's an overkill, because when you know for reason that this is a smaller dimension, why do you want to do a 3D model for it? 2D model is as good if it's done properly. Same thing there, even more important, because you're reducing not from 3D to 2D as in this case, but from 3D to 1D, 2 levels of dimensional reduction. Your models are going to become very, very effective, much, much more efficient. So that's essentially what we are trying to get to in terms of this entire course will be all about that. How we can have, instead of 3D models, which you might be familiar with from the COE 3001 deformable bodies, how can we go for AE course, in an AE course, in structural analysis meant for flight vehicle structures, can we deal with these kinds of structures, because this is all that you have as a airplane structure or a helicopter structure or a rocket structure or a satellite structure, missile structure. Every case you will have bunch of shells and plates and beams. And when I'm talking of beams, I'm talking in a much more generic way. Most people refer to beams as something which can take bending, but here we are talking of not only bending in one direction, bending in the other direction, but also torsion, like or axial loads, as in a helicopter blade, for example. There's a because it's rotating at a fairly good speed, you have a large centrifugal force, so the blade is getting pulled out, apart from the aerodynamic forces which are causing a lift, which is causing the bending as well, right? So, and because the pilot is operating the helicopter by changing the pitch angle of the blades, so what is happening is you're twisting as well. So in other words, there is because of the aerodynamic loads predominantly, there are other reasons also. You have bending because it's that's the lift which is causing the bending. Now there's a drag which is causing it to bend in the other way. Now there's, because of the pilot's controls, etc., and also aerodynamics, you have a torsion. Then because of the centrifugal force, you have a axial load as well. So in this case, it's very easy to visualize for a helicopter rotor blade, but that's essentially what's happening in all aerospace structures. Smaller or larger, one might be dominating, or a few kind of loads might be dominating over the others, but essentially you're dealing with all of that. So in other words, we're dealing with either 2D structures or 1D structures, which for not complicating the terminology, we are just calling shells, special case being plates where there is zero initial curvature, and beams, a special case being what is conventionally known as beams, where only bending is there. But in our beam, we will see there's not only bending, but axial load and torsion as well, and bending in both directions. Okay. Once we have a generic model like that, all of that typically is taught in a structural analysis course will become special cases of that. Just like I was telling you, from a material point of view, if you learn from composites, learn about composites, then metals will become a special case, at least until failure. Beyond failure, metals are more complex, as I already mentioned. But since our goal here in this course is only dealing with structures which are still healthy, which are still performing well, they have not failed, they have not undergone any damage or fracture, whatever. So therefore, it doesn't matter whether you have a composites model, you can still apply it to metals as a special case. Just like how, as I said, for a shell, from a geometric point of view, if you take a shell model, you apply zero initial curvatures, that is before any load is applied, there's zero initial curvature, then it's a plate. Okay, a surface becomes a plane when you have zero initial curvatures. Over and beyond that, yes, now I can bend this plate, and applying loads I can make this curve, right? So, but initially there is zero curvature. So plates are a special case of shells, metals are a special case of composites from the point of view of what we need to learn from this course. So keeping all that in mind, and also these are special cases when only axial load is there. If it's tension, or if it's a column, it's a compression, and here in this case it's bending, and in a torque tube, for example, it is torsion. So, but nonetheless, every one of them is a one-dimensional structure. So if I know how to deal with one-day structures, I can make it as a special case and deal with each one of them individually, put all the rest to zero. So that's the generic point of view from which we will be looking at this. And the reason why we are going to be doing this is that's the way the world operates now. We do a lot of projects for Airbus, Boeing, and few other aircraft companies, including helicopter companies like Bell Helicopters, HAL, etc. And all of the kind of things that they are working on a day-to-day basis is essentially composites, is essentially dealing with structures which can take multiple kinds of loads. So if you are familiar only with dealing axial load alone, or you're familiar only with dealing bending alone as separate problems, then how do you put them together? In a linear model, the principle of superposition will work, and therefore you can just add them up and get it. But unfortunately, life is not linear. Everything that you see in reality is non-linear, and therefore you can't just add Tom, Dick, and Harry's models and assume that it will work for your complex loadings kind of situation. So that's why we will see that, keeping in mind that this is an undergrad course and the level at which it needs to be, without going into the mathematical complexities of it, from a qualitative point of view, we will try to understand in the first half of the course how each one of these is dealt with in a generic sense, from a generic material, a generic geometry, and then in the second half of the course we will look at specific applications of that, and then you will see it's a child's game. Whereas most people, the way they handle this particular course and the way it is learned is to deal with each one of them separately. You learn your A, B, C, D, and the alphabet, and that's heading nowhere from when they go for the job market, be it in the industry or in academia or for higher education. It really is a sad plight when I go sit for some of these interviews at some of these places as an external specialist. Then you see that some of the candidates, the way they perform is really pathetic, and I don't have anything to blame them because that's the way they are taught. They're taught in a piecemeal kind of an approach, and when a question is asked from a more holistic point of view, even qualitatively they are not able to stitch things together. So which is why in the first half you will see it's very easy because I'm not going to have too many equations and things like that. Qualitative things I'm going to talk about, practical applications of that, and then you will be in a state of mind where you will be very familiar with the terminology that's used, and you will also be familiar with where each of these things go. And in the second half we will focus on just the axial load alone, or just the bending alone, just the torsion alone, just the different kinds of things, whether it's 1D or 2D structures. All of these will become very clear. So that's the broad approach that we will take. So most of our efforts in the first half will be towards the fundamentals of flight vehicle structures, and which means that we need to have a reintroduction, I would say, because you've already in deformable bodies been introduced to concepts such as stress, strain, how they are related to each other, etc., which forms to a large extent the body of knowledge called the theory of elasticity. So we will kind of revise some of those aspects because they are very, very important in structural analysis. Okay, and especially you, since you have not gone through these 3001, whatever we are going to do there will be directly useful for you, right? So, and there, as I said, we will be dealing with a generic material which is composites. So it's a composite analysis, and then we will see how that can be very easily specialized to metals which are a isotropic and homogeneous material, as opposed to this which is anisotropic and heterogeneous. In other words, different properties in different directions and different properties at different points within the same material, right? So once you know how to deal with such differences, once everything is the same for a metal, properties are the same in all directions at a given point, and which is isotropic, and the properties from one point in the material to another point in the same material is one and the same. So it is homogeneous, right? So when you know how to deal with heterogeneous anisotropic structures, dealing with homogeneous isotropic structures is going to be a child's play, because it's a specialization or special case of that, right? So now what are the kind of geometries that we will be dealing with? As I already mentioned, just to put it in words over here, one-dimensional structures, which, as I said, will be generically referred to here as beams. But be careful when you're going to literature or textbooks and things like that. People will be talking about beams as only those which will take bending. Okay, in our case, yes, they do take bending, but in addition they will take torsion and axial loads as well, okay, as long as they are one-dimensional structures. In other words, the cross-sectional dimensions are small compared to the length of the structure, right? So again, within the beam there can be many kinds, okay. You could have a solid beam like this, which you see there is material throughout the cross section, or you could have a hollow beam like this. You see there is no material inside, right? So now or a single beam in which parts of it are solid and parts of it which are hollow, like this particular structure, right? So the way we deal with each of these is very, very different from each other, and in fact very surprisingly it's the thin ones which give us more challenge, because the non-linearities will become very critical in this. But as I said, in this course we're not going to be dealing with non-linearities, so both of them will be quite easy for you as you go forward. Now in thin-walled structures, again you will have two types. One is an open cross section. So in other words, cross section is something when I cut through the structure you see a particular shape. That is what we call as a cross section. You're crossing through the and getting a section out of it, right? So now if I cut this beam that is running in this building over here, I would see that, imaginarily of course, I would see a rectangular shape. So that's your rectangular cross section, right? So now if that were a thin cross section, that could be in the shape of a C, let's say a channel kind of a cross section. So what you would see over here, let me see if it chalks. So what you would get out of this beam that I show here in the building is a rectangular cross section like this. But more often than not you will see in aerospace engineering thin-walled structures, and one of them, an example of, is this C section or a channel section. And the same thing when it is turned upside down, it's also called a hat kind of a configuration. So that doesn't matter, but essentially it's something like this. Another thing that you will see even more commonly in aerospace structures and also in quite a few civilian structures where weight is critical, and also many transportation industry sections, is what is called as an I section. So essentially along the length of the beam you're cutting it, and you find that this is what you end up with. The reason why these are popular, of course, is one, by changing the material from aluminum to composites, you have reduced the weight because of the lower density, but that's only a material solution. As I said, material is as important as the geometry. In fact, geometry is even more important. So if I can do the same job with this, obviously I have cut down more weight even if I have not changed the material, right? Or I have changed the material from metal to composite and also changed the shape, then obviously I have a double whammy there, and I'm getting both these advantages, okay? Similarly in the I section, etc., where each of these goes, I'm just giving two examples. There are many, many more. Let's say, for example, a Z kind of a section. This is again a very commonly used kind of a cross section, okay? Where and why each one of them is useful or important. Again, if you're looking at torsion as a predominant thing, then so if you look at this is solid, right? So in the kind of terminology that I'm talking about, all these three are open. First of all, thin-walled. Because if I call this as walls, essentially the walls are thin, right? In other words, the thickness that you have over here, let's say T, is very small compared to, let's say, the breadth B that you have over here, as well as the height H that you have over here, right? So now you are having T very small compared to B and H, right? So in all of these cases, however, you also see it's not only thin-walled, but it is also open. So in other words, it's not a closed kind of a configuration, which, for example, this kind of a configuration is. It's called a box beam. Again, very, very common in aircraft wings, for example. Or especially when torsion is very, very dominating load compared to all other things, you would have a circular, though this doesn't look very circular in my drawing, So essentially you're looking at a hollow cylinder kind of a thing. So these two are examples of, again, thin walled. Just like that, this is also thin walled, but this time the adjective that I'm going to use here, which was open in this case, is now closed. So in other words, if I go through the midline of this particular thickness, I can go around, I can go all the way around and reach the same point, right? So that's why it's called the closed cross section. Whereas if I start with the mid plane over here of each one of these arms or components of the channel, I start at one particular location, I end up at a different location, I don't close the loop, right? So that's why these are called open and these are called closed. And this is a very, very important terminology that you will see a lot, especially in the second half of this course, because that's what kind of makes aerospace or flight vehicle structures very different from the kind of structures that are typically used in civilian kind of configurations, where weight is critical but not as critical as in the transportation kind of engineering applications, right? So coming back over here, so what we are talking about is in this particular case, we are essentially, in terms of the loads that are there, we are talking of torsion, bending, and also shearing kind of loads. So essentially you're trying to, instead of a normal load, which is what you have in the case of an axial bar, or in the case of a column, you have an axial load, which is a normal stress. In other words, the stress, which is either tensile or compressive, is such that it's acting on a particular surface whose normal is along a particular direction, and the direction of the load is also along the same direction. So in other words, it could be a pull or a push, which is a tension or a compression, and both cases it's parallel to the normal to the cross section, and therefore these are called as normal loads or normal stresses. And therefore you are essentially dealing with that not only in axial kind of applications like columns and axial rods, but even in bending. So if I'm trying to bend this, what happens is at the top fibers will all be contracting and the bottom fibers will all be extending. Even though I say fibers, it's not necessarily composites, I'm just talking of a line even along a metal. So essentially you're talking of a line along this surface, it's getting stretched out when I try to bend it this way, right? The length of this is going to be increased, whereas the length of an element on this is going to get contracted, so in other words compressive. But in both these cases, though along the surface it might be different at different locations, they're all once again along this, because one is getting pulled, the other is getting pushed. So whether you have a tensile load or a compressive load, same way you have normal stresses coming out of this, and that's essentially what will be in bending. Whereas torsion and shear is entirely different. You don't have normal stresses anymore. You have on the cross section no stresses or very less stresses along the length, either in tension or compression, but parallel to the surface you have a stress. That is your shear stress, as you might have already studied, and that's something which will be dominant in torsion, as well as when you have, let's say, a lift distribution. That lift is going to cause not only bending, but is also on any given cross section is going to cause a shear as well. So you might be familiar with shear force diagrams and bending moment diagrams. Have you dealt with any of these before? Yeah. Okay. So essentially those are all normal, whereas in the sense that not normal in the sense of the English language, but you are talking of things which are having a direction of the load parallel to the direction of the normal to the cross section. Whereas in torsion and shear, these two will be perpendicular. So once again, the cross section's normal is coming towards you, but the load, the stress itself is acting perpendicular to that direction, and therefore it's a shear kind of a loading. And that's what you will see in torsion also, because for example in this case, if I'm applying, this is along the length, let's say extend this cross section throughout the length of this room, then I hold or fix one of the ends, let's say at the blackboard end, and towards the window end I try to apply a torque. So what's going to happen? This is going to twist. So when it's going to twist, obviously I cut anywhere in between, I'm going to have stresses which are going to be acting in the opposite direction to the torque that I'm applying, which is essentially going to be like this, which is going to resist that torque that I'm applying, so that it again, it's throughout. So I'm not drawing the whole thing, but it's something that is throughout to avoid. So now you see that the direction of the stress is along the plane of the board, but the normal to the board is perpendicular to the board, obviously, right? So these two are at right angles to each other, and therefore this is a shear, and shear stress as a result of torque, right? So we will see that as we go forward, there are two very different kind of animals that we are dealing with, but both of them are in the same zoo or in the same forest. There is a broader way in which we can approach both of these, even if it is normal stress in one case or the shear stress in the other case. So that's essentially what we'll be dealing with over there, right? Then, as I said, there are a few things which are not part of your course, but I will nonetheless touch upon these things every once in a while, not as separate topics, but as things which will be laced as we do this. Sometime whenever it is relevant, I'll bring upon certain nuances of this without going into the mathematical details. So those things that you need to be familiar with at the end of this course, you will see from a qualitative point of view rather than a quantitative point of view, are the failure criteria. So each material has its own way of failing, how the damage is initiated, how the damage is propagated. So essentially you're trying to see why that material behaves in a particular way. Is there a way in which I can at least postpone failure, if not avoid it? So that's essentially, these are kind of things that we'll be talking about over there. And the actual failure, how it happens, is it a fracture? So in other words, essentially a crack, and that crack grows, or the source of that is a load which is changing with time, so dynamic load which has a certain periodic behavior, or per se it might not look like a periodic behavior, but you can always convert a dynamic load into a series of periodic loads. It's like you have the Taylor series or Fourier series, so you essentially have each one of them is at a certain period, and some might be more dominant than the others. So essentially fatigue. So unlike a static load which will cause a certain kind of failure, a dynamic load will cause different kind of failure, and within dynamics itself there are many different aspects to it. One of them is fatigue, where it's a repeated cyclic kind of a loading or combinations of cyclic loading, and that's what fatigue involves, and we will very briefly touch upon it as part of the rest of the course. The other thing, again, though this is mentioned as a separate topic as part of your course, the way textbooks and the syllabus deals with buckling or elastic instability, of which Fanindra is an expert, that's another aspect of his work, is something that is very rudimentary. It will give us intellectual satisfaction, but at the end of the day, you're not going to be applying it the way we learn it anywhere else. So there's absolutely no point in going into the details of that buckling thing, but I will be covering how it is to be done in a more refined way in the industry and or in practice as part of what we deal with in the top set. And finally, there are certain aspects dealing with beyond fatigue, other kinds of dynamic loads which come under the purview of vibrations, which will typically, and each of them, by the way, can be a separate course. So failure criteria can be a separate course, fracture can be a separate course, fatigue can be a separate course, elastic instability or buckling can be a separate course, etc. Similarly, structural dynamics, testing, aeroelasticity, 3 separate courses over there. Okay, so dynamics involves essentially vibrations, single degree of freedom systems we start with, like a spring mass damper system, and then go on to multiple degrees of freedom, finite degrees of freedom to infinite degrees of freedom for continuous systems like the beams and plates or shells that we've been talking about. And coming to aerospace vehicles in particular, we not only have all of those structural loads and reactions from the material, but also the source of that is the aerodynamics that is happening there. And so you have aeroelasticity, both static aeroelasticity as well as dynamic aeroelasticity, and those are again fairly involved things. Not that these have been around, these topics have been around for many decades now, as long as pretty much the aircraft have been flying, and therefore these are all quite done and dusted kind of topics. It's something if you need to know, you can know, and therefore you will just go through it and try to find out and try to understand what needs to be done over there, right? So we will not get into the details of that. Once again, in terms of the actual implementation of the solution procedure, it's almost mandatory eventually in the industry to go to a numerical technique which is known as the finite element method, and there's a lot of knowledge in terms of how you get to the FEM. One thing is to know how you use a particular code like Abacus or ANSYS or Nastran, things like that. But the more important thing from an engineer's perspective is not just to know the user interface, but what happens within that. So there's a certain thing called the energy method. So there's a certain thing called the variational principle, where you're maximizing or minimizing certain things in order to get to that theory, which leads to an algorithm, and the algorithm leads to a coding, and then you have a finite element software built out of that, right? So we will try to look at some of those aspects when we are covering this, how to deal with one-dimensional elements or two-dimensional elements and things like that, which are all the building blocks of FEM, without going into details, because just like the others, that's also a separate course by itself, at least a few courses that you need over there. And then we will have certain parting remarks which are more from the holistic point of view, trying to combine all of these. So are there any questions or on this? Yeah. Method. Sometimes they use FEA to refer to analysis. Yeah, so the finite, yeah, not materials, method, the finite element method. So which is typically used to look at the actual underlying theory, the methodology, rather than the actual analysis itself, which could be for a specific thing. Both are entirely related to it. You need to have an FEM in order to get to an FEA. So we will not go into actual FEA, but we will look at some of the building blocks of FEM. Anything else? Any questions? Okay. Let's get going. Okay. So some of the things that I need to do anyway as part of this course. So as you know, I'm not this. So just to say what I'm not. In terms of the exams that you're going to have. In fact, I've already shared the final exam with you, and it's a fairly simple and straightforward way. And the reason why I'm doing it in this particular way is multiple fold. One of the things is, of course, the way things are going in terms of how we use this knowledge in the industry and academia, as I've been repeatedly saying already in today's class. But the other more important thing is we have a small bunch of in terms of the kind of interactive thing that we can have. It's much more possible for us to leverage some of the developing tool sets that are there. It's not only software like already mentioned during the previous slide, but also in terms of artificial intelligence. Okay, so AI has been playing a critical role, and I'm sure all of you have used ChatGPT or the equivalent of that, right? So, and how we utilize that for things that we do in a course and things that we do in the industry, there's going to be a lot of inputs from that. At the end of the day, remember that all of that knowledge is developed by human beings, and it's just collocated, and it's essentially much more easily accessible, more from a RAM or random access memory rather than a hard disk where you have to do a much more intricate search. Okay, so that knowledge is there for us, and it's there when we need it in much more easily accessible manner. We had that earlier, very long back. We had to go to the library to search for a book and then find the book, and within the book find the particular location where it was. Over a period of time, they all became available as PDFs and e-libraries, and so we just search much more easily and get access to a particular thing. Now we have a way of combining all of those information, putting it in a way in which is much more accessible. But human intervention becomes more and more important. As Spider-Man says, with more power comes more responsibility, right? So here you have a lot of power, a lot of access, a lot of information that you can readily access. If you blindly trust it, you're up for loss unless your luck is still with you, right? So you do need to see how you prompt, which is why the entire branch of engineering called prompt engineering is coming up, and it's becoming almost fairly well established now. And one is how you prompt it, what kind of questions you ask, and based on the responses it gives, how you change or tweak your question in order to ask it in a better way. And of course, with the GPT-4o, you're looking at omni, essentially text, images, audio, video kind of inputs and outputs as well. So, and this is rapidly going further. So at this stage, if we still try to do our learning and our courses and our teaching in the way we have been doing or where we learned it when we studied, it's absolute waste of time, waste of your time as well as waste of my time, which is why I want you to consult all of these. Unfortunately, some colleagues, both in this institute as well as others, would never allow you to use these things for their assignments or exams and things like that. I understand from their perspective the way they design their questions for the assignments and exams, but the way we are going to do it, we want to leverage those and see whether you can prompt better, whether you can, once the output comes, are you able to interpret it for your application or for your use, for the question that is asked by me or anybody else. Are you able to interpret it in a way that is directly applicable to that? It can, at least at the stage at which many of these AI tools are there, be it Gemini or GPT-4o or any of the Microsoft implementations of GPT-4, all of these are going to take you to a certain level at this point in time. Beyond that, there is a human intervention which is required. So let's use all of these powerful tools, but then let's see how we can actually make some sense out of it, make something that really addresses some of the fundamentals that we want to know. And in the course we can do this far, but at least this exercise that you do in that particular way will take you to a much better position in terms of how you deal with the things that you deal with in the industry. And in fact, from a philosophical point of view, this has not been very different from what has happened in the past also. Most of the exams that we have, unfortunately, in schools are closed book exams. Whereas in reality, when you want to apply a particular methodology to a particular problem that you face in the industry, your industry bosses are not going to say, no, don't consult any textbooks or no books, right? So you do consult that, and you in fact not only consult books, but you consult your colleagues, you work in a team, and everybody's input comes in and you try to come up with something better. And that's why we've been so successful as an aerospace engineering industry or ecosystem the world around, is because of that kind of a teamwork, that kind of an openness. And also, yes, industry has its deadlines, but it's not as stringent as your 3-hour exams. Somebody coming and pulling off the paper from under your hand or over the table, saying the time is up and you have to give the paper now, right? So you have a little bit of leeway, a freedom in terms of how you handle these things. So that's what I want to bring a flavor of, at least towards this course, and see that you use the cutting edge tools. You also make sure that you see where this is heading and where it goes, and see if we can have some takeaways in terms of when you get into jobs, how you will be utilizing these things, right? So as I said, the assignments are going to take all of the grading for this, and as I said, it's all going to be teamwork. You're all going to be working together, not competing with each other. And in fact, one of the stories that I'll probably say towards the end of this, which you're very familiar with already, is something that the other future episodes of which many people are not familiar with, will show you why teamwork is so very critical. And that's the way the industry works. That's the way we work in academia. I collaborate with so many people. Academia is an opportunity for individual development. There's a lot of freedom, but at the same time, you can do this much and no more if you're doing your entire career of research, working on your own favorite problems. But when you interact with others, and this I say especially because of my being influenced by Professor Dewey H. Hodges of Georgia Tech was my PhD advisor, who was the PhD advisor for Professor Mayuresh Patil as well. And he used to attend, as you're familiar with the brown bag lunches, talks of not only things related to structures or helicopters that he was an expert in, but any field, not only in our department, the aerospace, but also other departments. And sometimes some of the interactions he has had with the speakers have led to profound papers in subjects that are absolutely none of his expertise, or at least till that point of time. So what we might be struggling with day and night, getting stuck up with our research at some point, might be done in a routine basis by somebody else for a different problem. Okay, when you try to hear that and see intelligently how you can adapt it to your problem, you see that wonders can be worked out, and that's where I really need you to be heading towards. So that's why it'll all be teamwork over here, and you'll be presenting it in the I think I made a mistake in the email that I sent. I said the very next class. That's too much to ask for because it's very next day. So what we are going to have, whenever I give you an assignment, it will be due for your group presentation exactly a week after that. So if I give you an assignment on a Monday, then next Monday is when you will all be presenting something related to that, right? So same thing if it's a Tuesday to Tuesday, or Wednesday to Wednesday, or Thursday to Thursday, right? And we'll have, I think, about 5 or 6 assignments overall throughout the course, including your finals, which is also a takeaway kind of an assignment, which also you'll be presenting as a group, okay? Because the other thing, I'm sure with Georgia Tech students it's not an issue, but the thing that we see, and also IISc, we don't have too much of an issue, but many other schools which are not highly ranked, you see that though some of the students might be very good at understanding concepts, it's in terms of the communication, whether it's oral communication or written communication, where usually there is an issue, and typically and it's also the kind of scenarios. If you're going for an interview, the nervousness or whatever you have, and I think as teachers, I think that's an opportunity we have when we have these exams, instead of exams, assignments or teamwork and things like that, oral presentations of that. And there's nothing to be worried about. We're all part of the same team, and we want to see how we can develop together, learn together. That's essentially what we will try to do over here, right? So in that process, something which is very, very understated is the importance of unlearning. Okay, so most people are always learning, cramming. You're essentially trying to gather information, but some of the information that you have already gathered, you need to do some kind of a janitor work over there, try to cleanse that out, right? So because unless you do that, you're going to think that's as important as what I'm learning now. No, some of the new things that we are learning are much better than what we have already learned, and sometimes what we have already learned might even be wrong, okay, to put it at an extreme or a very strong word to use. But nonetheless, whatever we are learning is going to be more useful, and that can happen in a true sense only if you have learned what I specifically say as not so correct. I'm not saying wrong, but not so correct. And some of these might be courses that you have taken as part of your high school, some things that you have learned on your self-study, or even some courses in Georgia Tech, much more fundamental courses. But then when you try to get to higher and higher level courses, and this applies for my course as well. So something that you learn here, when you go to a more advanced course, you might have to unlearn some of the things that I'm teaching today, because I'm teaching you what's going to be the state, what is the state of the art today, okay? And what is the state of the art a year down the line might be quite different, and you might have to unlearn what I'm teaching now in order to do that. But at least you're doing the best that you can to keep up pace with the way these topics, these subjects are developing, and that's essentially what we will do over here, right? So the second aspect to it is, once you have some empty space over there, you're trying to fill that now in with the more correct. And some of these are unfortunately even a lot of professors continue to believe in, and books continue to be written which are published in 2024, and this is like the blind leading the blind, okay? So you have done that all your life, and you think that that's the only way, and you keep imparting to that batch after batch, No, that's not the way I like to teach, and that's not the way I like my students to learn and go implement it in the world. We do need to not get attached to what we already know. We have to always put it to a test. Yes, some of those things might be still very, very important. Some of the fundamentals don't change, but even if you look at the way physics has developed from Newtonian mechanics to Einstein's relativity or quantum mechanics and things like that, so many assumptions that we made about certain applications kept getting dropped in a different regime, either at higher speeds or smaller length scales that you are applying. We have relativity and or quantum kind of theories. So, right? So we have to be open to learning that. That doesn't mean Newton was wrong or whatever, but his applicability or range of applicability was limited, and we still use that for a lot of purposes, and very validly so. But if you're going to stretch your limits, then you have to go to the not so correct. And if that's true for physics, which are one of the fundamental sciences or the fundamental science, obviously in engineering, this has to be done even more at an even more shorter length scales, much more rapidly, right? And then you learn the more correct, and that's essentially what we will do mostly in this course. But we will also look at how it enhances your ability to apply this assimilated knowledge. Here we will see it through simple examples in the homeworks assignments, but more so get you prepared or ready for whatever kind of jobs that you eventually go to in the industry or the academia. So that's essentially okay. Any questions on this so far? I already uploaded the. Yeah. So right now you might not know what I'm asking for there, because I'll be conducting a class more towards, let's say, 3/4 of this course. So to tell you more clearly what I am looking for over there. But as I've already shared the playlist with you for the previous cohort, the 2023 batch from Georgia Tech, which attended the same course, I've not changed anything in terms of the questions. Okay. But I really want a response which is much superior to what they have done. Okay, so nothing to say about them or their capabilities, but more importantly, I think as part of evolution, Darwin's theory of evolution, it's not stopped with the human being. We as human beings want to get better and better, not compared to another human being somewhere else, but compared to ourselves. What I was yesterday, I want to be better today. What tomorrow, I want to be even better than that. So, and that can happen only if you learn from the mistakes of the past and try not repeating that. So it's from that point of view, I just shared that playlist with you. I want you to go through the way some of the homeworks have been done by them and try to go a level further, not just incremental improvements, but a level further to make sure. So because that's already been done, and why should I hide it and say I want you to work from scratch, right? So if that is already there, that is an inspiration for you. That sometimes, and that's something sometimes inspiration in a negative way, that you can see, oh gosh, I could have done it far better, right? So that's the spirit that I want you to develop, and so that we can continue our evolution as individuals and as a team to the extent we can. Yeah. Any other questions on this? Okay, once you are accessing their Teams, apart from the YouTube playlist, it's also in Teams. All the files are there, the homeworks as PDFs and the slide decks that I have. It might, of course, depending on the pace at which I lecture, because it's always flexible for me, I do it spontaneously. So it might be that I finish a class which I completed in 2 classes for them, maybe in 1 class for you, or the other way around. So bear with me on that in terms of the overlap that happens. But nonetheless, it's pretty much the same set of slides that I have, and it's all already available for you as files. They didn't have that advantage because I was developing the course along with the teaching at that point of time, and therefore some of these slides I didn't have access to at that point. And so to be fair enough to that. Okay, so as far as this, I think we'll probably stop with this. So just I pretty much covered most of this in the in whatever email that I sent out as part of Teams when I sent the links for joining the virtual class. So all homeworks, as I said already, are going to be team games. We are essentially going to be in team games and in structured peer coaching. So it's integral to the learning. So essentially, don't think of the homeworks as evaluating what I've already taught. Sometimes I might bring in certain concept which is just next to whatever I've already taught, so that I want to see, are you able to push the limit beyond what I'm just talking over here or showing you on the slides, and take it the next step by yourself. Okay, so especially the later homeworks will be of that kind, and that's integral to learning as I perceive it. Okay, so as I said, the only competition is not the other team members or even the previous cohorts, but your own past self. Essentially, you want to become a better person yourself overall, and especially in application to structural analysis problems. Okay, so some of the tips that I could give you in terms of the strategizing this whole game, because I think of it as a game. I think of whole life as a game, and therefore this is a part of that game, a small part, a smaller game within a larger game, right? So as I said, just like how you would do in the industry or as professors later on, some of you in the future, I want you to use all the resources that you can access. Okay, why leave out? As long as they're relevant for whatever you're dealing with, utilize all of them, be it large language models, apps, books, internet, forums like Quora, etc. Many specialized forums for mechanics and structural analysis, etc. Fanindra, the other lab mates might be able to give you examples of that. And then, of course, your friends within the team and outside as well. And even if some of them are enemies, fine. So whatever, you are essentially trying to access as much information, but at the same time, the information overload should not make you irrelevant for that. So that's why I underlined this word relevant over there, because information is like an ocean which keeps coming towards you, and as much as you want, whenever you want, from so many different sources, but you have to be guarded in terms of which to use when, right? So then I also want you, even if you're using, let's say, GPT-4o and ChatGPT or anything else, I want you to cite them, okay? So we want to have it as a learning process, okay? So what kind of questions did you ask, and what kind of reply did you get? How did you tweak the question? What exactly did it answer, and how you are interpreting that answer to solve the problem? So I want to understand the process. I want to walk you through that. You want you to walk me through that process that you have followed. And maybe if I have a suggestion or two, I would say maybe you could have done this, probably it would have helped better, and that might help you with a future homework. Or maybe I'm learning from you in terms of how more innovatively and intelligently to ask questions, which is why I said this is a part of not your learning, but our learning as a group, and that's where I would like you to go, right? And so therefore, I want you to give the specific references, even if it's a book or whatever, so the apps that you use, etc., and give the specific input and the utility. You don't need to read through that whole thing, but at least it's there for the class to see, and if necessary, we will go through some of the lines of that to see how that can probably be tweaked for a better output overall, right? So we want to see the specific input and the utility, and also most importantly, because the way at which all of these, in spite of their humongous capabilities, they are still developing tools, as you know, right? Especially the LLMs, right? So what are their limitations, and therefore how you kind of overcame them. Sometimes they might hallucinate, sometimes they might give you very silly responses, sometimes they give you completely irrelevant responses. So how do you tackle that? How do you go beyond that and still extract what you want? Or some cases it doesn't work at all for a particular thing. How you go back to your traditional sources of information and try to get that, right? So, and over my quarter century of, at the risk of giving away my age, anyway, the beard should have already given it, over my quarter century of teaching, I have learned that the best way to learn is to teach and or to mentor. Okay, so that's the process that I've followed, and the process for me is much more important than the eventual outcome of the process. So as long as you're doing the processes right, I think if the outcome is not there today, it will be there tomorrow. So it's important that you keep refining your processes of how you encounter any kind of challenges that come through, right? So the problem allocation basis for this entire thing is the core competency. That's essentially what you're seeing, that each of you have unique capabilities which you have developed and refined over the years, especially during your high school and the Georgia Tech years. And I want to see how that will be tackled. We have kind of run out of time today, but or maybe I can, because I think we still have a little bit of time. I have just a slide on that. Aesop, as you know, was a great fable writer, and many of his fables have been very popular amongst kids. But these are things that unfortunately are seen as something as like moral stories for kids and things like that. I see that as something of a learning for entire life, and you the way you perceive them as you mature, as we grow older, is that we see it in a very, very different light, and it gives us certain takeaways for us. And the one that I'm going to refer to here of this many fables is the hare and the tortoise, right? So the hare and the tortoise story. So that's what we're going to look at. So as I said, no individual scores, not only for that assignment, but any of them. And then it's not goal oriented, as I said already. It's going to be process oriented. Unfortunately, this has become a cliche. Everybody kind of uses goal oriented. We have done that for a long period of time. It's helped us in a certain way, but it doesn't take us beyond a certain level. It's only when you understand the process and try to make refinements over that the goals are also achieved as a collateral, as an automatic benefit, rather than something that you're chasing all the time, right? So it's important to be in the process. That way automatically you are in the present as well, rather than chasing something in the future, right? So that's why the final answers are also provided for all your questions, as you'll see in your homeworks. And then I think there are some exceptions to that, okay? And also because you have an opportunity to see the previous cohorts videos, you will have a certain set of answers, may or may not be right? So the slides are only to be used as the skeletal prompts. So when I describe the homework or the assignment here, it's more like a skeletal prompt, but in the oral description is where, so even your slides that you come up with for a presentation. So the homework that I give today, you're coming up with something on next Monday, you will present it along with a set of slides, right? So I don't want those slides to be too wordy. I just want you to focus more on your oral presentation of that, and use that only as something that you fall back to if you have a line of thought that you forgot or something like that. So use it only as a prompt for you. You prompted the LLM, now you come here and you're trying to get prompted yourself by looking at a slide if there's a something that you forget on the way, right? And because we are process oriented, we do not want to skip the steps, okay? Because the steps are very, very important. It's not just the final result which is important, which is anyway in many cases given as part of the solution. We want to see the step. What is the logic you use? What are the arguments you use going from one step to another? And which is why I request you not to skip steps, even if they might be kind of silly or too simple. We can rush through them but not skip them, rather, right? Now this is a very, very important thing, and in fact a big chunk of my course will be on assumptions in structural analysis. Which of them are, as we called in the previous slide, not so correct, which of them are state of the art today, and therefore which of them we need to drop off, which of them we will pursue further. And the same approach I want you to do as far as your homeworks are concerned as well. I want you to explicitly state, not think that, okay, you imagined, okay. Many of these things, unfortunately, because of muscle memory especially, we are assuming and we don't even know that we are assuming. My advisor used to tell to one of my juniors, not Mayuresh, somebody else, that if you don't know, that's fine. Okay, if you don't know something, that's fine. But if you don't know that you don't know, then even God can't help you, right? So that's very, very critical. Okay, so all of us have a finite knowledge at the point at which we are, and we need to know what we don't know. because then we can pursue or seek that. Okay, otherwise we will be living in ivory castles thinking that we know it all, right? So that's why it's important that some of the assumptions that you might be making because of muscle memory, without even knowing that it's an assumption, I want you to bring that out. Okay, challenge yourself. Yes, if I had not made that assumption, even though I had not thought about it in that way, maybe I would not get to the next step. And that's where not skipping steps helps as well. Okay, sometimes we skip steps only when we are making some wrong assumptions that we have so much convinced ourselves to with, right? It's like telling a lie. Okay, you're telling a lie and you repeat that lie 100 times to 100 people, and then you start believing that lie yourself. Okay, so it's like that. Some of these assumptions, it's unfortunate, but that's the way the human mind works, that we have started making them, and we take that for granted anyway. That's true, and then we go to the do very advanced things, but then if the very building block is shaky, then the foundation is shaky, obviously the building is not going to work well, right? So which is why the assumptions that are involved are very, very critical, and assumptions at every step. Instead of listing out all the assumptions, like we list out a bibliography at the end, we say all these from which I got the information. No, I want it at whether it is the citations or whether it is the assumptions, I want it at between the steps, one step to another step. What are the new sources of information? What are the new assumptions that you've made, and which leads you to the next step? It's okay if it takes a little more time than otherwise, but this way you are learning something that's going to be important for you as in the entire life. Because as far as this course is concerned, grades are concerned, it's not an open secret. You'll all get good grades. Okay, so don't worry about that. I really want to utilize this quality time that you have. Of course, the cultural experience in India over the long weekends, 3 days into 10, almost 30 days. But while we are in the class also, I want you to take away something that you will remember and cherish for life. And I've had, fortunately, like Fanindra, many of my alumni from my lab, why should I say many, almost all of them are still in contact with me, contact with the lab. Some of them mentor our current students, and essentially that process is happening because they cherish what they learned over here, and they are utilizing some of that knowledge, maybe not be in exact words, but the process itself for something else. Whether they are in the teaching profession to teach the way probably much better than I teach, but also in the industry, the way they handle new projects, new challenges, the teamwork that they do, everything has been phenomenally unique or different for our alumni compared to many other labs alumni. So I essentially want you to do that. So I have just about 10 minutes, so with which I will give you this homework for today. You don't need to write down anything, because anyway all of that is the slides, the slide deck that I've already shared. So as part of that, so you will see that what we are dealing with is one of the famous fables of Aesop, the hare and the tortoise. As you know, the hare and the tortoise has, how many of you have heard this story? Yeah, pretty much all of you, right? So you know the first episode when the hare fails and the tortoise wins the race, and just people say slow and steady wins the race, right? So you know up to that, or you know beyond that as well? Any of you have heard beyond that? Yeah, okay. So that's episode number 1. Okay, so there are 3 more episodes to this whole story, so I'll not bore you with the first episode, since you already know that the hare rested in between and therefore didn't win the race. The tortoise, who everybody thought would lose the race, eventually won it, and they say slow and steady wins the race, right? So next, the hare thought about it. Obviously it messed up something, so it wants to redo that. So it asks for the race once again. Okay, so this time obviously, see, it's a hare is essentially a sprinter. It's not a marathon runner, right? So it wants to do quickly, and then if it feels tired, rest and then go. But now it challenged itself and wanted to complete the race, even though it was a fairly long distance from the starting point to the end finish line, and it did it in one shot, and it obviously won the race compared to the tortoise. So this is something that is obvious to especially your generation, or even my generation for that matter, that yes, being steady is good, but why should I also be slow, right? Why should it be slow and steady? Can I not be fast and steady? Okay, which is what the hare did at that point of time. It understood its strengths and its limitations, that it's a sprinter more than a marathon runner, and then he wanted to see, even though I'm a sprinter, let me take a marathon challenge for a while and let me do it. Okay, and it completed that. So essentially you're trying to learn about yourself, what your strengths and weaknesses are, and can you extend your strengths and reduce your the domain of your weakness. So that's how the second race ends, with a different winner. Right now the tortoise got thinking, okay, so I won the first race, he won the second race, so let me see, can I change the game rules a bit, tweak it and make a different kind of a game where I will still win. Okay, so then he called for a race again. The hare laughed at him. After having lost it so badly, you still want to race? He said yes, and now we have a different finish line. Okay, so fine, it doesn't matter for me wherever the finish line is, however farther or however nearer, I will still win the race. And the race started, and as the race started, once again, of course, the hare was way ahead of the tortoise, and when the tortoise came up to the part of the race track, it saw the hare. The hare was standing over there. It's not sleeping like in the first episode, but it was just standing, staring. What had happened? The tortoise very intelligently thought about his own strengths and therefore included a water course in the whole way. So there's a river to be crossed before the finish line, and the hare, this particular hare at least, didn't know how to swim and therefore got stuck up over there. The tortoise, even though it took a long time to reach that bank, from that bank to the other bank, it just swam across and finished and won the race. So essentially you have to understand your competencies. Okay, many a times we are not aware of our own individual competencies. We want to get to that competency, right? So next, that the story didn't stop over there. Okay, then they discussed with each other. This is going really interesting. So the last and the fourth episode. So here they decided, okay, we have been challenging each other. Why not we work as a team? Okay, so let's keep the same finish line like the last time, the same starting line. In the first part of it, I, the hare, will carry you, the tortoise, on my back, and we will reach the first bank of the river very fast. And then you, the tortoise, carry me, the hare, and we will swim across and reach the finish line. So as a team, they were able to leverage each of their competencies and then reach the finish line much better. As a team, they did much better than each of them individually. 2 plus 2 was resulting in something much bigger than 4, right? So this particular thing has repercussions not just as childhood stories or morals and things like that, though I probably related it in that particular way, delivered it in that particular way, but this could be things that we are doing with on a daily basis, pretty much any challenge in life. But I want to put it in context of this course, structural analysis. I already told you 2 important factors there, the material and the geometry. Many times we are at loggerhead. I have these 2 materials, which material do I want to use? Think of them as the hare and the tortoise. Okay, why use only one of those materials? Can I use both of those materials and come up with something better? That's the composite, my friends. So that's the composite. It has a fiber, it has a matrix. Each of them have very, very different properties, as different as chalk and cheese and chocolate. So essentially you're looking at doing something which is better that you can do, but something that you're not good at, can you bring in some other material which can do that, which is what the fibers and the matrix work together as. Similarly, in terms of geometries, we talked about all these geometries. These guys are really good at handling torsion. These guys are really good at handling bending. This is probably very good at handling axial loads, both tension and compression. But in reality, in real life, many of these structures will be having not only torsion, but also bending and axial loads. And sometimes these axial loads might get into tension, sometimes into compression. So can I use combinations of these? And that's where we come to a very important concept in flight vehicle structures known as semi-monocoque structures. If you don't understand this scheme, don't worry. Monocoque essentially means a single shell, like an egg shell, right? Semi-monocoque is not a single shell, but multiple shells coming into contact with each other in a certain sense, and therefore taking the load together, and that's essentially what we will do. So, as I said, structural analysis involves two important things, material and geometry. Though I might be repeating this, I'm repeating it for a purpose. I'm stressing on this because this is the very crux on which the entire course is built. Please remember, most people will have you believe material is all it has, but no. The reason why we are doing all of these is geometry is equally, if not more important, and therefore you have to make certain material choices, you have to make certain geometric choices, and at each stage, if you can do this as a team, then you will be doing better. Okay, so let me quickly complete this slide, so which most of it I have already told. So many of us have heard or read this fable, and like most fables, it starts with a catch line, once upon a time, right? Already we have a quantity which we deal with in structural analysis and also in dynamics that you have already dealt with. Is a very important factor. It's an independent variable, just like space, spatial coordinates that we were talking about, let's say x1, x2 and x3. You have a t, which is a fourth dimension that you're dealing with, and there's that. And when you say once upon a time, you're fixing a particular instant in time, and that's what we deal with in many of the differential equation problems, where you have, instead of boundary conditions, we have initial conditions. Whereas in that race, your start line and finish line were like boundary conditions for that particular process to happen, right? So there are certain initial conditions. So next is the tortoise and the hare. So these you can think of as elastic bodies, even though the tortoise shell is fairly rigid compared to the hare's skin and or muscular structure. So nonetheless, every body, at least up to a certain limit, has a certain elastic behavior, and we will see exceptions to that a little later. And then the next thing what we are trying to do is, these elastic bodies are seemingly unconnected or unconstrained. The tortoise and the hare have nothing to do with each other. Even if you look at the theory of evolution or the food chain, whatever you are looking at, probably they're not directly connected, but there is something that we can do together. That's what we want to do. So, and similarly in a structures problem, there's certain things about joints, certain things about constraints. Like for example, in this case, we say it is fixed. In other words, both the ends are fixed. They cannot move. They cannot rotate. Similarly, when you have something which is on a balance like this, then you essentially say it is hinged or pivoted, and when it's pivoted at both the locations, you essentially say it is simply supported. So all of these are kind of constraints or connections that you're bringing up, and when you have to argue between them from a design point of view, which is what analysis usually leads to eventually, you are looking at about an argument between the hare and the tortoise. Essentially, you're looking at a feasible solution space that you have to search for solutions in for your structural analysis problem. Now, there is a criteria, obviously, in order to choose which material. For example, we said it has to be light-weighted. If of the same strength and stiffness, we want it to be lighter in weight, so the density plays a critical role. So there's a criteria that is, and so therefore you bring in certain performance metrics which are associated with who is faster, right? So then you decide the methodology choice. So in other words, based on the argument that we have had, what is the criteria, what is the objective function that you want to maximize or minimize, but that's just the end goal. As we say, our course is not goal oriented but process oriented. In order to achieve that goal, we have to have a process, and therefore the methodology comes into picture, and this is what Anai was asking about earlier. FEM is finite element methodology or method rather than the analysis itself. So that methodology or the algorithm is very important before you go into a code implementation. These days your LLMs are doing a fantastic job in terms of writing codes. Yes, they don't write the whole code that you want, but at least parts of it. Earlier we used to search for subroutines, user subroutines which are in the open space or in GitHub and things like that, and take them. But now you can make it write what you want and then probably connect things at least with some human intervention at this point in order to be able to do that. But essentially there's a methodology choice that goes with it. So what do the hare and the tortoise decide? They want to decide to settle with a race, okay? And that race is in structural analysis, which is what we will end up this whole course with, is called as variational principle, okay? These variational principle or variational methods will minimize the energy or the total potential energy. There are many ways of stating it, Lagrangian or Hamiltonian, etc. But without going into too much of details on that, that is important because the syllabus of your course says that finite element methods and energy principles, that's what we are talking about. Okay, so we want to do some kind of an optimization, some kind of maximization or minimization, that is important. Okay, so then once we have that, we have decided to take this particular approach, then obviously we need a specific route that we want to go on, and that's essentially the hare and the tortoise. All the yellow ones are the actual story and the red ones are obviously the interpretations, one possible interpretation towards this particular course. There could be many other kind of interpretations, which is where I want you to let your minds open up. They say think like an open box, but there's no box here, so why even go for an open box? That's a box beam, but here you're talking of human mind, which is completely open, and you have to challenge yourself and try to get to that. So if you're talking about a route, I had already talked about one episode that you already knew and 3 episodes in which the route was slightly different. The third and the fourth, it was the same, but the approach was different. But at least 3 routes were there in that particular problem, and essentially what you're 2 routes rather. So first of all, we have to start with something. So that's where the iteration begins, and that's the initial guess that you want to iterate with. And then you start raising this, that's essentially the solution process itself. And most of the solution process is already taken over by computers for a few decades now. Okay, so what is more important for us is to focus on the problem definition, the problem formulation. Once we have done that properly, most rudimentary computers these days, leave alone supercomputers, can do most of your solution processes quite effectively, the kind of software packages, etc., that are available, as long as you choose the inputs appropriately. Otherwise, of course, it's garbage in, garbage out, right? You don't want that. If you have done the problem formulation appropriately, then the problem solution is going to be a child's game, right? So finally, as I said, this is what is going to be your assignment. Do take a look at what your seniors have done, and then try to do much better than that, because you're not competing with them, but at least you're trying to evolve yourself better than that, and that's an existing body of knowledge. What you want to do is beyond that body of knowledge, and that's essentially what you're going to work on. Okay, so and I want all the 4 episodes covered, the 1 episode that you already knew about and the 3 episodes that I just talked about, and these are stories that are available on the internet as well. I don't think IISc gave those 3 episodes. It's a kind of a logical extension that some innovative thinkers have done, storytellers. And so if you have not heard me fully, of course we'll be putting up this video recording as well, so you can take a look at that, this parts of it, and then you can see how for all of those 4 episodes, how you can do this yellow-red extension in terms of structural analysis problems. Any questions on this? Yeah, a very good point. Yeah, so we are talking about this one, right? So essentially what you're looking at is, see, whenever you're trying to search for a solution, you are if you put yourself completely open. For example, let's start with a very simple example. I'll take you to that. Let's say you want to answer a question in structural analysis, but your entire library is open to you. You start searching each and every book. No, right? You go ask the librarian which is that section, or you yourself know from the numbers or whatever catalog, you know there's a particular bunch of books which are related to structural analysis. That's what I will study. So in other words, you're reducing from an infinite knowledge space that is there to a smaller space. Okay, now coming to structural analysis, the way we are doing that is we are trying to do an optimization problem eventually. In other words, we are minimizing the total potential energy, etc. We don't want to be searching any and every possible thing. For example, this hare and tortoise problem, we know the kind of possibilities that are there. There is a land path, there is a water path. There cannot be a flying air path, Okay, so neither the hare nor the tortoise. If there was a bird along with that, maybe we could have taken a large bird at that, let's say an eagle or a vulture. We would have taken probably a part of the course being that as well. So now I'm eliminating a rail track or an air space or even vacuum space. I'm essentially saying these guys have to breathe, they have to be on land. At least the tortoise is amphibious, it can be on land or water, and therefore this is the space in which I'm going to search for my solutions, right? So that's essentially what is meant by a feasible solution space. So the actual solution space, once you start the problem, might be infinite, or it might be very large. If not infinite, it might be finite but very large. But it's not practical to search that, and it's highly inefficient to search in that large space. You narrow down your space, you know there are certain constraints based on the problem, based on the challenges, based on the capabilities of these animals in this case, but the materials in your problem or geometries in your problem. So based on that, you know you don't want to search beyond a certain thing. Okay, for example, I will search for all these kinds of beam like models. I will not search for, let's say, in a particular problem, plate or shell models, or a three-dimensional brick like model, okay, where length, breadth and height are all of the same order of magnitude. I am not going to be searching for that. Okay, I am interested in a lightweighted structure. Let me go for this. Yeah, does this answer your question? Yeah. Anything else? Okay, so let's break for lunch. Sorry for holding you for 10 minutes late. So let's go ahead and meet at 11 virtually tomorrow. Okay, Fanindra will be there. Yeah.
So one more thing, I think the slides that we have
Uh-huh.